Good morning. I'll try to stick to the 20 minutes given, even less. I just want to give an idea of the methods used for estimating vaccine efficacy, this time, which, as Valeria mentioned, it's an important problem. Basically, when we have vaccines, when we have epidemics, we have a period of time over which we have infections. Infections here are represented by little x's, like events happening over time. And the purpose of our vaccine simply is to decrease the frequency of infections over time. So if we have many infections, we want fewer infections. That's all. That's as simple as that. And we have different approaches to it. We can tackle it from different mathematical and statistical points of view. We will do very simple approaches today. We will review vaccine efficacy for one-on infections, which is a classical, for example, COVID-19 vaccine. We will see an example from the Pfizer paper on the COVID-19 vaccine, and then we will mention what happens for vaccines with recurrent infections, so more than one event of infection. For example, when you have recurrent events like exacerbations of a certain infection, and you want to reduce the number of exacerbations. All right, so vaccines are clinical trials, and I've been doing clinical trials for some years now. In clinical trials, we study efficacy, safety, and possibly individualization of therapies, and we do comparisons sometimes with a placebo, sometimes with a standard of care. So, for example, the very important paper for our times is the publication of the results of the first COVID-19 vaccines based on RNA technology. Very important from a biological point of view because it was a very innovative technology, and also from a statistical point of view, there were some novelties there. The experimentation time, the one I mentioned before, remember, study begins, study ends here. So the experimentation time was around late summer 2020 in both sides of the hemisphere. It was a randomized, placebo-controlled, observer-blind, pivotal efficacy trial for an orphan drug, what we call orphan drug. There were no vaccines for COVID because COVID was a new illness, of course, and this was the first time, so it was an orphan drug with no parents, and orphan drugs have a preferred way to be approved more quickly than other drugs, in case they show efficacy. You can see you can see what was that? Function effect, I have to say. What was that? How do we take off this, You can
move it, yes.
You can see some cartoon here showing with some details of the virus. Actually, the results are very obvious. You can see here in this plot the cumulative number of infections under the vaccine, the red curve, and cumulative number of infections under placebo. So there was no standard of care. So placebo was a control here, and it's obvious. There's no need for statistics here. It's obvious that the vaccine was superior, but still they did a formal, of course, it's necessary as per protocol. They did a formal evaluation of superiority of the vaccine with respect to placebo. And the interesting thing is that it was a Bayesian analysis. So if you read the details here, for example, look at this. Down here, there's credible interval here because they're not the estimation of vaccine efficacy was done with a Bayesian credible interval and not with a confidence interval. All right, so let's see what they mean by vaccine efficacy. The vaccine is at the intersection, let's say, between clinical trials and clinical medicine and epidemiology. So epidemiologists look at incidence rates all the time, how bad things happen over a population, and the usual way to compute incidence rates is just, if you read some epidemiology book like Rothman is a very important epidemiology standard. It says, or if you look at this American governmental publications, they say number of new cases over a period of time. So it's not a parameter, it's defined in terms of an observed number of cases, so it's a statistic, but still we understand that this is an observed incidence rate. So it's an estimate of a theoretical population incidence rate. And vaccine efficacy is defined in terms of rates, incidence rates. So what does incidence rate, I will get to that in a minute. What does incidence rate mean? Well, what happens between study beginning and study ends is all sorts of different cases. We've been talking about sensory. Professor Papengom just talked about censoring just now, and censoring is the same thing here. Censoring may happen with time to event data. So the first person up there got into the study, and then after some time, he or she was infected, but the next person, the second person, got into the study at some later time and finished before when the study ended, that person was still not infected. Same for, so the third person got into the study and then died after a while. So survival or infection time for this person was clear, and so on and so forth. And actually, sorry, I made a mistake. The third person was dead but not infected. Sorry. The third person died for other causes. So we don't count the third person as an event. We count it as a time, but not as an event. So sorry about that. Same as the fourth person. The fourth person got in the study when the study begins, and that person lasted until the end without being infected. The fifth person was infected, and so on and so forth. All right, so the simplest way of representing this is to stick together all these times and consider it as if it were a homogeneous Poisson process. That's the simplest way to tackle it. Of course, it's very naive, but that's what underlying the definition of incidence rates in an epidemiology book. From a mathematical point of view, it has to be Poisson, homogeneous Poisson processes. So when you stick together all these pieces of time, you get a time which is expressed in person years, which is a preferred unit for epidemiologists, person years. All right, so if you take this simplistic point of view, then when you compare a placebo or standard of care versus a treatment, you get two homogeneous Poisson processes with two lambdas. So you compare the two incidence rates. Let's call them lambda now, because I'm talking about the population rates, not the observed estimates of them. And so these are theoretical parameters. And therefore, finally, vaccine efficacy is defined as a population parameter in terms of the incidence rate ratio. Actually, 1 minus the incidence rate ratio. And it represents, the idea is that in the long run, you will save a proportion equal to vaccine efficacy of non-infected vaccinated participants who would have been infected if they were not vaccinated. So what you save in terms of infections when you give the vaccine. And that's the idea of vaccine efficacy. Very simple, 1 minus the incidence rate. Now, of course, when you estimate this, so when you come now to data, and you count the number of infections in the vaccine cohort, the number of infections in the placebo cohort, surveillance time in person years, and so on and so forth, then you have the naive or maximum likelihood, if you like, estimates for the two incidence rates. If you take 1 minus the ratio, you get an estimate of the vaccine efficacy. And then you have several methods to compute either confidence intervals or credible intervals for vaccine efficacy. There's some references here. UL 96 is an important paper. Then there's a book recently, just because, maybe just during COVID, just before COVID, there was a book coming out on vaccine efficacy. Okay, now one of the methods is Bayesian, and that's exactly what was used for the Pfizer protocol. Now, I wanted to stress something that you may have thought about it, but I want to stress this. The three lines I wrote down here. Notice that all this implies a constant rate of infection and uniformity sensory. This may be quite different from the real world, for example, in the case of the recent COVID-19 epidemic situation. What do I mean here? What I mean is that there has been all sorts of many papers and books and studies related to the development of the COVID-19 epidemics over time. So it was, the famous peaks. Every one of us was concerned with peaks and troughs and valleys of the contagious curve over time. There's nothing like that is represented here. Here, when we compare a treatment versus a control, we just compare to homogeneous Poisson process. So it is as if we were taking a short time over which we assume that the rate is about constant, that the rate of contagion is about constant, but it's different for the treatment and the control. And that's why it comes down to an incidence rate ratio, which we estimate using the obvious things. All right, so when we look at this exact method condition on the total number of cases, which is reported in UL 1996, it's a standard credible interval for Bayesian, for binary observations with a Bayesian conjugate prior, so a beta prior for P, except that it's revisited in terms of vaccine efficacy. So if you look at it, if you consider just the number of cases in the vaccine cases, number of infections under vaccine, number of infections under control, and the condition on the SV and SC, which are the total surveillance times and the total number of cases, you condition on them, you use them as if they were constant, then everything is easy. The distribution of XV is binomial with certain parameters. You do a binomial beta conjugate analysis, and you get an estimate of I get posterior mean for vaccine efficacy and a posterior credible interval. That's what they did in the Pfizer BioNTech protocol, and you can see the results in the paper I mentioned before. Now, we could be a bit more refined than this. So my contribution to this, which I thought about, was that conditioning on SVSC and the total number of cases is kind of simplistic. There is some information contained in the total surveillance time for vaccine, total surveillance time for control, and the total number of cases. So if we were to write the full likelihood can be written recursively in this form. The likelihood of the surveillance times first times the conditional likelihood of the total number of cases times the conditional likelihood of the number of infections on the vaccine given the total number of cases and the surveillance times. And in the Pfizer, the exact method condition of the total number of cases only uses the third piece, doesn't use the first two pieces. So what I tried to do was to see whether it makes any difference to use the first two pieces. First two pieces are not obvious, but we can do some mathematical statistics in it if we make some assumptions. So again, each infection process is homogeneous. You have a lambda for vaccines and lambda for controls. No loss to follow up. No informative censoring, in other words. And if you take if you consider that the recruitment process is uniform over time, then you can do some computations. Actually, assumption number 3 was criticized by a referee, but it's a stupid assumption. We can, instead of making it uniform, we can make it exponentially, or almost exponentially, it doesn't matter. So I will change it, okay, but it's not the point of my contribution. The point of my contribution is to explore whether there is some information contained in the times. Now, if you do this, you get a full Bayesian hierarchical model, which can be represented as a DAG. It's a very simple model. It can be done easily with standard software. No need to do your own code like Luca likes to do all the time. Whereas I like to use standard pre-packed software because it's that lazy. And there are some reasonable choices for the default values. I'm not going to bother you about this. And you get something which is slightly different from the Pfizer paper. Although, of course, the vaccine efficacy was very high in any case. So we have minor changes in the results. It's not the numerical changes that matters, it's the method. So here, instead of having this 90 to 97, which was what was published in the paper, you get something 89 to 97% using my method, but it's not so, it doesn't make a lot of difference. Okay, it's conceptually it's important, not practically. And if you have, standard vaccines have a vaccine efficacy which is much lower than 90%. So with other therapies, you may be happy with 40 or 50% vaccine efficacy. In that case, it may make a difference. Okay, now I want to finish mentioning in the second short part of my talk. I want to finish talking about the case of therapeutic vaccines, which is something Martina is working on. My PhD student Martina is working on with GSK, for example. So as I mentioned before, each patient now may have more than one time to event. So they may have recurrent observations, for example, recurrent exacerbations of the same illness. I may have crisis over time. And the purpose of a vaccine, like on the right in the treatment group, we have an efficient vaccine if we decrease the frequency of infections within each patient. So we have recurrent events here. That's why I asked Papam before if in his approach he could do lasso with recurrent events, but he didn't consider this case. He considered another grouping of observations. All right, so here again, if you do the standard thing, you have 2 Poisson processes. Now things are a bit more difficult because it's not clear what to do. And in addition to this, you may have censoring which may be informative. So if people feel like they have too many events, for example, they may think they are in an inferior group and they may stop taking the drug, for example, which is exactly the case of informative censoring. Now, we struggle with this informative censoring, and of course, now, in case of independent censoring, you have the usual things, just have some summations of counts here and summations of time, it's the obvious thing, of course. But in case of informative censoring, things may change. So that's what motivated GSK to sponsor the PhD by Martina. Martina has been struggling with this informative censoring and different ways to cope with informative censoring and take care of it. So correct your estimation of vaccine efficacy using the fact that we do have some information about informative censoring. For example, okay, here's some base estimation. There's no need to talk about this. I just want to conclude saying that with GSK was interested in informative censoring with a non-parametric approach. The Cox approach that Papangom was mentioning before. I wanted to, in order to understand things, I wanted to consider a much simpler and parametric case, very simple, nude, the simplest nude example of informative censoring, which is when both the recurrent event process, so the point process giving exacerbations, and the censoring event here, the censoring mechanism, share a common parameter lambda, both in the vaccine or in the control group, up to a proportionality constant gamma, which is irrelevant. Now, in that case, we can actually make it, make explicit maximum likelihood computations, and it's interesting the fact that you also have to count the number of censored observations, and you have to count them as if they were observations, which is kind of natural. Obviously, if you think about it after the fact, it's, it makes sense. And this, so this would be then the maximum likelihood estimate for vaccine efficacy. Well, actually not for vaccine efficacy, but for 1 minus vaccine efficacy, which is the incidence rate ratio. In case of censored observations, you also have to count the number of censored, whereas the naive estimator will be biased because of informative censoring. And based on this, several considerations may be done, and that's what Martine is doing while finishing her PhD and extending it to the non-parametric case, semi-parametric Cox regression case with inverse probability weighting as a method to compensate for the bias. Okay, thank you.
Thank you, Mauro, for this very interesting talk. I can ask you, the people in the audience here in the room, if you have questions or comments, you want to take a vaccination, or we are not ready, but at least we have some information. Sophie, you have a question.
So the first one is regarding the non-parametric extension you talked about. It's fully non-parametric using like kernel estimator.
At the very end?
Yes.
Which estimator?
Kernel estimation.
Kernel, no.
Empirical estimation.
No, it's semi-parametric. It's not semi-parametric, like Cox, because they have a treatment as a covariant. That's basically.
Yeah. The other question is, so you do this work based on Pfizer. Do you have any comparison regarding the other kind of vaccination?
The other ones were not.
AstraZeneca
was not Bayesian. It was a standard survival approach with estimation of basically of a log odds ratio, of a log hazard ratio, similar to this, but frequent is not Bayesian. So I considered this because I wanted to look carefully into the Bayesian approach so that you have this full likelihood that it's interesting to work with.
Because I'm wondering if AstraZeneca is less efficient than the vaccination than.
Not because of statistics, no.
Yeah.
It depends on.
In a statistical point of view.
No. It depends on this wonderful idea that BioNTech and this lady from Hungary, her name was. I can tell you. There was a lady, I will tell you the name later if you ask me. There was a lady from Hungary, and since the 90s, she believed that RNA could be used as a vector for vaccines. Then neutralized and used as a vector. Nobody believed her. She went to America. She was not supported by anybody for a long time. And then after a while, BioNTech sort of believed in her, and then COVID came, and she was so successful that she made a lot of money in BioNTech and being bought by Pfizer, being supported by the American administration and the British administration and the European Union in 2020. They poured a lot of money into research. But there was a wonderful example of a biological intuition, genius really, by this lady. I can tell you her name. My wife always tells me her name. She told me the story. It's very interesting it's a very interesting success story for a lady, for a biologist, and for some recent research intuition.
Thank you.
I have one question for Gasparini. Okay, how did you choose the prior distribution? Because here, in general, a binomial prior distribution is used when the observation follow a Poisson distribution. And here, what is your guidance to?
They had, the Pfizer did that, and they did a standard choice. They said we are sure we can start with a prior efficacy of about 30%. That's the least we can reasonably expect, because they had very positive results from preclinical studies. So they say it cannot be less than 30%. And 30% is already interesting enough for vaccines. And then, of course, it shot up to 90% looking at the data. So 30% was an estimate of the average, prior average. And then for variance, they chose basically, I'm not sure, they choose a variance which was practically equivalent to a few observations. They knew prior observations. They knew that they were going to observe hundreds of events. So a prior with a variance equivalent to a few observations is not so informative.
Okay, thanks.
Okay, any other question? Okay, if not, then we thank all the speakers of the day. Mauro, if you want to say some general comments from the point of view of the statistical group on the conclusions of the communications of today.
Yes, okay, so everything started with music, which is good because it was a visit by Valeria and our PoliTo, which is a student team in our department. And they went to Senegal and they had some nice musical exchange with local musicians there. And then always, as always, when we go abroad, we try to make some connections between music and mathematics, especially because Valeria got interested into this, and she has a couple of presentations on popularizing the connections between mathematics and music. Nice. This is also something we give to undergraduate students as sort of little thesis sometimes, bachelor thesis or master's thesis. So she got connections with some mathematicians, esteemed mathematicians. Three of them well, 2 plus 1 we saw today. Professor Dabo is working in France, but she's also from Senegal originally. And so that's why we decided to have this meeting, because other professors in our department do have some connections with other African countries. It's something of interest for us from an exchange point of view. So Professor Gatto on Monday will, again, because Sophie is visiting us, there will be some meeting with some politicians also, a representative of Namibia. Other people for example, they go to a summer school in Kenya. Enrico cannot be here today, but he will organize a summer school in Kenya on chemical reaction networks from a probability and statistics point of view. And using also this network of MAMs, this network of mathematicians, high-level mathematician network of African mathematicians. So it's all very interesting activities. And specifically today, we wanted to talk about possibility of exchange. Maybe our professors visiting Senegal, one of the 3 professors who spoke today, for example, or vice versa, us having some visitors, either young professor or young, professor, doesn't matter if they're all young, or young researchers, postdoc or PhD researchers from Senegal visiting here. There are some funds. So the ambassador, the attaché, the cultural attaché in Dakar this morning mentioned some possibilities to partially fund some exchanges for a few months, for example. For example, if a person from Senegal doing a PhD in Senegal wants to spend a few months here, there will be some money. Of course, the exchange rate is not favorable, I guess, to Senegal. That's why we are willing to. Carvalho mentioned that the embassy is willing to give some money, and we also have some money here to have some hosts, to hosting some postdocs or docs at the last year, during the last year, for example, during the second year of PhD. So maybe you can mention some other. And so there was a way to know each other, and as a way to know each other, I'm listing here what my PhD students did in the last few years, starting from 2014. Moreno is the only one who stayed in a university environment. All the other ones are so far, all the other ones who are not out yet, some of them who are still in here, for example, Luke and Marco, but all the ones who are out now are in the pharmaceutical industry, and that's obvious given my interest in clinical trials and statistical methods of clinical trials. I think it's always good to have an industrial sector that can absorb your students. It's very good also for young people because it gives them two possibilities, either you choose one or choose the other, but you can always keep a second choice as an escape in case things don't work. It's always good to have options. So Gael started up a startup, a consulting startup. After many years, she worked in the pharmaceutical industry in Novartis and Servier, and the other French, remember the name. But anyway, now she has a startup, very successful startup. For the first couple of years, she already was able to give us also our students some things to do. Jose is in Novartis, big pharma, standard clinical trials in Basel. Elvira is in Boehringer Ingelheim. Lydia is in Bayer Berlin. So I'm very, very proud of all these people. And Martin is finishing. Oh, sorry. Martin is not Martina Gannis, Martina Amongeva. She's not sponsored by Servier. She's sponsored by GSK, as I mentioned before. I mentioned about Martina before, using my vaccine efficacy. I wrote these slides very quickly last night when I was on a train. Sorry. And then we had the last four people are not done yet. Two of them are here. And again, they're working on some biomedical clinical trial related topics, but there are also topics which are very good also from an academic point of view. So there is no forced option for any of them. It depends on how things will go. And we do have some possibilities to host, as I said before.